And we're going to get started. So before we dig too deeply into biogenic materials, I just want to give a quick introduction to the Carbon Leadership Forum for people who are new to us. So the CLF is a program based out of the University of Washington, working to radically reduce carbon in buildings and infrastructure to enable a more just and sustainable future. We're building for a better planet through 3 primary strategies. We are improving data and methods, informing effective and just policy, and building a community for impact. To build that community for impact, we have a network of architects, engineers, contractors, material suppliers, building owners, policymakers, associations, and other industry stakeholders through various forums, including our online community platform, active focus groups, regional hubs, the NGO roundtable, and more. Together, we enable research, investment, and action to reduce the embodied carbon in buildings and infrastructure. To date, the network has evolved into a vibrant, engaged global community of over 6,500 professionals from across the building sector, academia, nonprofit, and government groups representing 200 cities from 33 countries across the world. This collective action model is dedicated to accelerating the transformation of the building sector to radically decarbonize buildings and building materials through collective action. Online at the CLF community, our members convene around subject-specific focus groups to share resources, questions, updates, and other information related to embodied carbon. So that's something to look out for if you aren't already engaged. And at a more local level, we're supporting a movement of volunteers who lead regional carbon leadership forum hubs to focus on issues relevant for your communities. So I believe that now we have 30 active hubs across the world, with the most recent one getting off the ground in Bangalore or Bengaluru in India, as well as Minnesota. So if you're interested in joining a hub or starting your own, please visit the CLF online community for more information or reach out to us. And before we move on to the logistics, I must also thank the organizations that support the Carbon Leadership Forum in this work. So your sponsorships enable a movement of thousands of leaders to reduce embodied carbon in buildings and infrastructure. There you go. Now I see it, Chris. Okay, so now on to the logistics. Just mention of trade names or commercial products do not constitute endorsement or recommendation for use. So please note that the opinions, ideas, products, or data presented by speakers in this session do not represent members of the Carbon Leadership Forum network or constitute endorsement by the network. So our goal is to introduce topics that help participants think and talk about building industry strategies for reducing carbon emissions attributed to building materials. So the flow for today's webinar, we're going to spend about 40 minutes with presentations from our 3 speakers. And then after that, we'll have about 15 minutes to share comments, questions, any other insight that may have come up during the presentation. We'll have a recording of the webinar available afterwards. And another thing that I should mention is that we're doing monthly happy hours on the months that we don't have webinars. The next happy hour that's going to be taking place in July will be focused on biogenic materials. So if we don't get to discuss everything at the end of today's webinar, there'll be an opportunity in a few weeks to come together and in a little bit more of a casual space, talk about these topics. So now to introduce the speakers. Today we'll be hearing more about current and future applications of biogenic materials in construction from 3 smart and inspiring speakers. So this team has been consulting together on this topic since January of 2020, bringing perspectives from an academic materials research lab, a materials education and construction school, and an architecture design firm. So first, we have Wil Srubar. Wil is an associate professor of architecture engineering at the University of Colorado Boulder, where he leads the Living Materials Laboratory. He received his PhD from Stanford University in 2013. His research aims to create and grow carbon storing material technologies for the built environment. His work has been highlighted by the New York Times, NPR, and the Washington Post. Dr. Srubar is also a co-founder of Aureus Earth, a carbon offset marketplace for building projects, and Prometheus Materials, a construction biotechnology startup. Next, we'll have Kriegh Magwood. So since 2011, Kriegh has been a director and teacher at the Endeavor Center, a not-for-profit sustainable building school in Peterborough, Ontario. In 2019, he helped to establish Builders for Climate Action and has been leading development of the Beam Carbon Estimator tool for low-rise construction. He's working closely with many levels of government to develop embodied carbon benchmarks and regulatory programs, and helping developers and builders figure out how to reverse climate change with their buildings. Chris has authored 7 books on sustainable building and is co-editor of the Sustainable Building Essentials series from New Society Publishers. His new book, Building Beyond Zero, New Ideas for Carbon Smart Architecture, is co-authored with Bruce King and will be available later this year, so keep an eye out for that. And last, we'll have Dr. Julie Kriegh. So Julie founded Kriegh Architecture Studios in 2000. She has special expertise in sustainable residential projects, multifamily communities, and custom commercial projects. Recognizing that buildings are a key solution to climate challenge, Dr. Kriegh researches and designs solutions with a focus on energy efficient buildings. So this really relates to operational carbon, sustainable materials. So this then relates to embodied carbon, and high performance design and construction methods, which relates to prefabricated and passive house. Using her design and research knowledge, Julie is currently a sustainability consultant at the Mount Vernon Municipal Library, a project manager with the UW Carbon Leadership Forum, and the UW's CBE studio instructor, so College of the Built Environments. Dr. Kriegh received 2 AIA Upjohn Awards and an EDRA Core Award for Research Excellence for her doctoral work, understanding the key values underpinning pro-environmental behavior in the built environment. She's an avid bike rider and gardener. So without further ado, I'm gonna hand it off to Will to get us started. Dr. Srubar.
Thank you, Anthony. It's really great to be here today, and especially wonderful to be presenting with my wonderful colleagues, Julie and Chris, this morning. I'd like to kick off today's conversation by really painting a broad picture of the landscape of biogenic carbon storing material technologies. We're of course here today, Chris, next slide, because the materiality of the built environment, as we all know, has and will continue to have tremendous environmental consequences. Most people are surprised to learn that concrete is the second most consumed material on Earth after water, and that steel and concrete production alone contributes more than 11% of our global greenhouse gas emissions. These facts, coupled with the fact that we will be building a New York City every 35 days for at least the next 40 years, all that means to say that the environmental impacts of materials matter, and they matter now. And we're of course talking about specifically about upfront embodied carbon, the carbon emissions associated with the manufacture, transport, and installation of construction emissions, so that pulse of emissions that occurs. Climate scientists now agree that we simply cannot just reduce carbon emissions. We have to systematically draw down and store carbon permanently, or at least for decades, in order to avert climate disaster. And so the grand opportunity that we're talking about today is that we can offset some of the emissions of some carbon emitting materials with biogenic carbon storing materials to actually transform buildings into carbon sinks. There are a number of materials that can store carbon, and we'll get into some of those, but thinking about this very fundamentally, there are 2 primary mechanisms we building material scientists can exploit to store carbon in buildings. The first is of course photosynthesis, and in fact all photosynthetic biomass, every tree, plant, seed, even algae, contains about 40 to 50% elemental carbon by mass, and that equates to about 1.83 kilograms of CO2 that is required for producing 1 kilogram of dry biomass. We have equations in LCA tools that calculate this physical quantity of biogenic carbon. That's what you see kind of when you run your tally models and your Athena models. And really the key strategy here is to keep the biogenic carbon locked up for as long as possible so as to not re-release it in the short term. This temporary lockup has real economic and environmental benefit, as Chris will explain in a few minutes. The second mechanism that I will mention is carbonate mineralization, in which CO2 or bicarbonate is reacted with calcium oxide or elemental calcium to really fix carbon dioxide in a mineral form. So this is usually, the product is usually limestone. And there are technologies that use CO2 to chemically mineralize calcium carbonate, but there are also emerging technologies that biologically mineralize calcium carbonate, thereby categorizing those technologies as also as biogenic carbon storing materials. So what is the current landscape of biogenic carbon storing building materials? I'll first highlight some basic categories of materials based on photosynthesis, and then highlight a few technologies based on carbonate mineralization. When I speak to architects and engineers about biogenic carbon storing materials, the conversation usually starts in the forest. So our primary association with biogenic carbon storing materials are wood products that sequester and store biogenic carbon. So dimensional lumber, OSB, plywood, glulam, mass timber, cross-laminated timber. Certainly those sequester and store carbon. In addition to wood products, though, what I want to think about today during this session are other materials beyond wood that demonstrate promise for building applications. So for example, straw, hemp, or bamboo, agricultural residues or purpose-grown fibers are really examples of raw biomass resources that can be very rapidly grown. One thing to think about here is that some agricultural residues are just left in the field to decompose, and it's a source of biogenic carbon storing materials that we can transform into building products. If we actually use land to purpose grow materials, we have to be very cognizant that it's going to compete with food production really for some land and water resources. So really, in terms of the hierarchy, looking at those agricultural byproducts of what's left over after we harvest the food and ag products really is the primary source that we should be looking to. And Chris will also talk a little bit about some products that are derived from these certain materials. In addition to these fibers, algae-based materials offer tremendous advantages as a raw material resource. So algae are already cultivated at scale for food, fuel, and pharmaceuticals. It is now being exploited by a number of different research labs and startup companies for building materials. And personally, I believe this is a grand opportunity. My research lab does a lot of work with algae because when you consider, Chris, next slide, when you actually consider the land use carbon efficiency of algae compared to other photosynthetic systems, algae are pretty much unmatched. So what I'm showing here is a graph of the land use carbon fixation efficiency and tons of carbon dioxide per hectare per year. So this is land use. You think of this as land use efficiency. And note that this is logarithmic in scale. Algae and just the doubling time of algae, which is on the order of hours, that translates to an exceptional carbon fixation efficiency of about 2 orders of magnitude higher than forests. Of course, forests create very strong, stiff materials, and algae is not necessarily that. It has to be transformed into other types of materials. But you can see just clearly with all of these materials, these are natural mechanisms of carbon storage. And really the challenge is making sure that materials derived from these raw material resources are cost effective, and that we lock up the carbon that is fixed in these systems and in this biomass for decades. If you go to the next slide, Chris, we're not crazy. We're not the only crazy researchers thinking about algae systems and integrating those into buildings. If you do a quick Google search, you'll find other examples of integrating algae with building systems. Arup has done some work in this space, as well as other researchers around the world, especially those in Australia, are really thinking deeply about this. At this point, I want to shift a bit to discuss materials that leverage the mechanism of mineral carbonation. And a good material to highlight to really facilitate this transition is hempcrete. So for those of you not familiar with hempcrete, hempcrete is a hemp lime composite that carbonates over time. It is a product that takes the woody stalk of the hemp plant, kind of grinds that up. It's called the shiv, and mixes that with a lime-based binder. That the lime-based binder then continually carbonates and mineralizes over time. So there's really two aspects of this carbon storage. One is in the woody stalk of the hemp plant. The other is in the CO2, the carbonation of the lime. So in addition to hempcrete, there are many companies that have invented technologies based on carbonate mineralization. I don't have time to go through all of these, but what I've done is categorize them really in terms of their approach to carbonate mineralization. Those on the left-hand side are using a chemical approach to reacting CO2 with either elemental calcium or bicarbonate. And those on the right-hand side are now using biological approaches to fix carbon in mineral form. So these would represent a new class of emerging biogenic carbon storing material technologies that should be on everyone's radar. My last slide, we would be remiss if we did not mention the various and often disparate ways to account for biogenic carbon in whole building life cycle assessment. This is not necessarily the primary focus of our presentation, because we are focusing this discussion primarily on biogenic carbon storing material technologies in general, not the carbon accounting. But in all honesty, this topic of carbon accounting for biogenic carbon can easily be the topic of an entire webinar series. But we'd like to at least highlight and discuss some of these approaches, and happy to bring this back up into some of the discussion. The most common approaches for including biogenic carbon in whole building LCA include actually not including it. So number one is to just negate that temporary storage of biogenic materials and just simply not reward that biogenic carbon storage potential to any life cycle stage A, B, C of a whole building life cycle assessment. Some results do not necessarily reward any life cycle stage. They simply report it as a separate quantity. I'd say the most common approach is what's called a kind of a +1 - 1 approach. So some whole building LCA studies do reward the biogenic carbon storage capacity of materials to analyses that consider life cycle stages A or even AB system boundaries. But if you look at the entire system boundary, then it is subtracted at end of life if stage C is considered. Next click, Chris. Some whole building LCA practitioners only take this approach really if the wood is from a certified forest and the carbon balance is maintained in the forest. Next bullet. But where I think the nugget of some of where the disparate results really arise is in our looking at the entire whole building LCA, the whole building life cycle, and the end of life scenarios that must be assumed to estimate the net emissions of biogenic materials at the end of life. So whether it is landfilled, recycled, reused, or incinerated, various tools make different assumptions, and this causes the most disparities in whole building LCA when considering biogenic carbon. Next click, Chris. There are other emerging, really new approaches, including dynamic LCA and what is called GWP Bio. And these methods integrate the forest carbon balance over time, over the lifetime of the building, along with really dynamic LCA gets at this time-dependent life cycle inventory for refurbishment and replacement, knowing that processes and practices will improve with efficiency over time. Next click. Here's where I think a lot of the frustration lies. Ultimately, it is up to you, the LCA practitioner, to choose a method and report the results. You just have to be very clear and transparent with how you report the results and what assumptions you have made. My last point is that there are other emerging methods that are being brought to the conversation, including what are called ton-year accounting methods or discounting methods that are really looking at valuing the actual storage time, the time value of biogenic carbon storage. And what's an advantage of these approaches is that it completely circumvents the biogenic carbon accounting issues I brought up in 1 through 3 here. It's really just looking at the storage lifetime of the biogenic carbon in a building and assigning value and a carbon offset equivalency to that. With that, I will hand it off to my colleague, Chris. Take it from here. Chris, I think you are muted.
You are correct. Thank you. And thanks for that lead in. It's always a pleasure to present with you and Julie, and I've certainly enjoyed the work we've done together. And I'm sort of going to pick up right from where Will just left off, looking at sort of mapping out what some of these carbon accounting scenarios look like. And in the first one here, we're going to sort of look at all 3 life cycle phases, A, B, and C. And essentially, the whole building life cycle assessment tends to come down to a number at the end of the building's lifespan. So you calculate all the emissions that happen from the very beginning over on the left, and by the time you get to whatever that building's lifespan has been decided on, over at the right, there's a sort of a number that represents those emissions over at that side. And as Will pointed out, with the biogenic carbon, the line sometimes is straight, it's sometimes not, but essentially, if you look over at the end of lifespan and the carbon, was, either accounted for or not accounted for at the beginning, and it's accounted for coming out at the end, we quite often see that the difference between a sort of biogenic material or a conventional material often look quite similar at the end of the whole building life cycle assessment. But what I want to do is, my animations are a bit funny here, but is sort of look at this scenario with the time value that Will was mentioning kind of built in. And here we see on these red lines the sort of steps of emissions that would happen as materials are harvested, manufactured, transported, and the building is built. And then I've shown it as a static line. There's probably a few jumps in this line as materials are repaired and replaced. And then at the end of lifespan, some either emissions from landfilling or some credit for recycling. But that's how we end up at that sort of red dot at the end of the building's lifespan. If we trace a biogenic material, the path looks really different, and there's a lot of difference that sort of arises from tracing it this way. So there's often a small burst of emissions from the planting procedures for biogenic materials. And then there's this period of photosynthetic drawdown. So that's what Will was referring to. As these plants grow, they're pulling CO2 out of the atmosphere and using that carbon to essentially make themselves. The length of time of that photosynthetic drawdown is going to vary a lot depending on the material. So if that's a tree growing in the Canadian boreal forest, it could be 80 years. If it's grain straw growing in the American Midwest, it could be 3 months or sort of anywhere in between that. So, there can be quite a difference in time scale on that photosynthetic drawdown. And then essentially biogenic materials do tend to release emissions through those same steps of harvest, manufacture, transportation, and construction. But the vast majority that I've looked at end up in a sort of position of net storage at that point. So if you count the carbon that they've taken out of the atmosphere, subtract the carbon that went back into the atmosphere during production and construction, you end up with a sort of net negative number, or, you know, over the lifespan of that material in that building, there's less carbon in the atmosphere than there was before that happened. And then there's a whole bunch of end of life scenarios that we can sort of talk about later. But what's important to note here for the climate, and, you know, we do want to make sure that our analysis in life cycle assessment is serving the purposes of the climate, is that these emissions on the conventional material have sort of hit their peak, you know, at the time the building was built, and they remain in the atmosphere driving climate change for the whole time that building is standing. And so really, it's the area under this line that is the climate impact, because those emissions don't sort of happen and go away. They happen and they stay in the atmosphere, and sort of year after year, they continue to trap heat. Whereas for the biogenic material, it's that area over that green line, between the green line and zero, that is meaningful storage. That's CO2 that was not resident in the atmosphere over that period of time. And so it's a very different sort of look at accounting for biogenic carbon when you consider the value of that residency of either carbon in a building or carbon dioxide and other greenhouse gases in the atmosphere. It's also, you know, important to note that even though we decide that a building's lifespan is 60 years or 80 years or 100 years, the emissions are in the atmosphere for longer than that. They are sort of gradually decaying, but that building will continue to have climate impact beyond the date that we set as its end lifespan. And also that the emissions that are going to emerge from the biogenic material, even if they all come out and go back to the atmosphere, all of that carbon, really it's the same carbon that came out in the first place. There's no sort of net addition here. It's just sort of putting the carbon back into the atmosphere. And obviously we would like that to happen as far into the future as possible by, you know, different ways of making sure that material stays in use, by being able to reuse or recycle whole building assemblies or biogenic materials. And that really, you know, at the end of even where we consider the building's lifespan, it's really just those, you know, A-level emissions that become additional at the end of the building's lifespan. So Will referred to sort of ton-year modeling for this, and this has been looked at by climate scientists. And what this graph is showing is that if you look at the residence time of carbon dioxide in the atmosphere, and you look at the carbon storage of say putting that carbon into a building material, that 1 ton of carbon stored in a building for about 46 years is the equivalent of averting that 1 ton of CO2 at the beginning of the building's lifespan. So essentially, within the lifespan of a typical building, if we're talking about materials that would reside in the building over its entire lifespan, at the sort of 46-year mark, that carbon the storage of that carbon has had the full meaning of taking a ton of CO2 out of the atmosphere. And just a quick note on forest carbon. Again, this is something I know the CLF has spent a lot of time on, and there are full webinars about this, but just in general, with forests, there's the sort of a lot of external issues to consider, which we can sort of sum up by saying that if the carbon pool of forests, that's the growing trees, the dead trees, and the carbon that those trees put in the soil, if that pool is getting smaller in order to make the pool of carbon in buildings get bigger, then nothing has really happened to the benefit of the climate. So with forests, the carbon stock in the forest has to increase as our timber use in buildings increases, or counting that biogenic carbon as good for the climate, may not be the right thing to do. What's of interest to us in this presentation and in the work we've been doing is looking at all the other sort of non-forest biomass that's out there to be used, because for the most part, other than forests, a lot of this material has done that carbon drawdown from the atmosphere, but it's very sort of short-lived, and it's going to return back to the atmosphere either through burning or decay in quite short order. And so what we're sort of suggesting is that we interrupt that cycle by putting a whole bunch of that carbon into buildings for however long we can. If that's 60 years, that's great. If it's 200 years, that's even better. But essentially, by stopping that material from that carbon in all of those materials from going back to the atmosphere immediately, we are providing a really important service on our way to trying to fix the climate crisis. And we know that there are billions of tons of this biomass available for the building industry to use. A study that was done in the US, this was mostly looking at biomass for energy generation purposes, but it could just as well be bio-based building materials, found anywhere from over 600 million tons to over 1 billion tons of this type of material being produced in the United States every year that currently is not being put to any other use. So the feedstock for fueling biogenic building materials is quite well understood and documented, and there's a lot of it. And to put that in a bit of perspective, this is globally speaking now, but there are over 2 billion tons of grain straw grown annually on the planet. So we plant all of this material, we grow it all, and we sort of chop off the seed head at the top and leave the stalk of straw. And so in essence, that planting that farmers are already doing is drawing 4 billion tons of carbon dioxide out of the atmosphere every year. So that agricultural product or that group of products, grain, is withdrawing the GHGs from the country of India on an annual basis. But right now, the vast majority of that just cycles right back to the atmosphere very quickly. And so there are lots and lots of ways that this one particular product can be used in buildings, including lots of different companies making straw SIP panels for walls and roof, using it as blown insulation, using it as compressed panels for interior partitions, using it as continuous exterior insulation, acoustic panels. And in Europe in particular, the sort of size and scale of buildings that are being done with straw-based materials are getting quite large, and it's sort of exciting to see the progress that's being made there, and would be great to see the same kind of thing start to take root here in North America. Oh, I'm just going to end on showing you a little case study of a building I was involved with here in Ontario, Canada. This is for Trent University. They needed a new forensic science lab, and they decided that they wanted to make it an ILFI zero carbon certified building. And in particular, the folks at Trent were also keen to not just try to address the operational emissions of the building, which is the focus of that program. So the building has, I think, 46 kilowatts of solar on the roof and will meet the sort of zero carbon on the operational side, but they were really keen to look at it from the materials side too. And so we worked with them to do an assessment of the materials. This is a sort of A1 to A3 study of the materials in the business as usual building that they were going to build. And this little 4,000 square foot building was going to have over 200 tons of CO2e emissions associated with its material palette. And after we worked with them on selecting as many appropriate biological materials as we could, we got that building down to the point where it actually had net storage of about 6 tons of CO2e. So over 200 tons of difference between the way this building was going to get built and the way it was built. and just sort of showing that these kinds of products and materials are out there today. This building was code approved and built and met all the requirements of a public building. So things we used included expanded glass aggregate as subslab insulation, which is not a carbon storing material, but it is a material with a very, very low carbon footprint compared to other subslab insulations. A Nexem wood chip ICF block, and a really high slag concrete mix in the foundation and in the slab. None of those things are biogenic or carbon storing, but what they do is they reduce the overall carbon footprint of the building, such that when we start adding materials like these just biofiber hempcrete blocks for the exterior walls of the building, hemp bat insulation, wood fiberboard insulation, and cellulose roof insulation, by the time we put those materials in, while doing everything we could to keep the carbon footprint of the rest of the materials as low as possible, that's how we got that result. And I just want to also show you here that the result for this building, if we excluded storage value in the timber and the wood products, is just under 6 tons. So from 211 tons down to 6 tons, even if we're not including storage in wood, if we're only including the storage value of the agricultural byproducts and other waste stream materials in this building. So that, to me, it's really exciting. It shows that this is not a sort of future dream, that we really could be making buildings that are close to or at zero or carbon storing right now today, if we chose to do so, and that the material options for doing that are kind of developing quickly and well worth your consideration if you're in that role in this field. And with that, I will turn it over to Julie to wrap things up.
Thanks, Chris, and thank you, Wil. As both my colleagues have said, we've spent the last year working on these topics together. If you want to advance the slide, Chris. And what we've thought about is this whole building LCA and what's possible in terms of carbon storing buildings, looking at it incrementally. So I'm going to walk you through a little bit of the way we've been thinking about how to create this paradigm shift in the way that we look at buildings and building construction. If you want to click through the next couple of, right there. So our work has been focused on looking at these hotspots, which Chris actually just described nicely with his Trent building model. You're looking at the concrete, the insulation, the structural framing to get that significant reduction in embodied carbon in the next 2 to 3 years. So that's the kind of time frame we're looking at. But if we want to go further, it's really the critical key is looking at these biogenic carbon storing materials so that we're way below that line, as Chris has mentioned in his slides. And what that takes, actually, our team has really gathered around this idea that we're creating a carbon storing building ecosystem. So it's not just about one piece here or one piece there, or an architect or an engineer or a materials scientist or construction builder. It's really this ecosystem that looks at assemblies, structures, the site, and community scales. Next slide, please. And where does that start? So in order to accelerate this kind of change, what I found in my doctoral work, looking at what motivates people to engage at these different scales. So people are pretty reticent to change, and environmental psychologists have acknowledged that there's a lot that goes to it. So if you can start a project by really investigating the values that people in the industry are bringing to the table and investigating in terms of creating change, you can hold on to those values and hold on to that vision, so that the ideas that you have at the beginning of the design, business as usual, moving into this paradigm shift will hold until the building actually gets built and then is there for its lifetime. So on one of our projects, we've been looking with a company that is really excited to lead by example and dare to be disruptive. So that's like a first line item in our value system, our value structure. They are interested in influencing materials production, so that's another scale, but really taking a holistic approach. How can what they do ripple out into our communities? How can what they do, what they sponsor, what they're interested in, holding those values and visions, be something that impacts surrounding communities and both locally and globally? So that's really important in terms of being future ready. So to be future ready, we need to be thinking not only about what we do here in one community, but globally, and then one design here that could be disassembled and reused. As Chris has said, if we can keep those materials within a building ecosystem, it stays flexible for the future. Next. So Chris coined this idea of stacked benefits. So we look at the values-based, that is necessary for this paradigm shift, and stack up all of the different ways we can approach the problem. So to the left, you can see we can do one-to-one substitution. So materials that are on the market today, and what impact might they have. We can look at near-term products that are out, that are almost at scale, and what impact might they have on a building scale. Or we can really take this leap, what we sort of term as the quantum leap, into investigating new materials and daring to bring them on board and create situations where the acceptance of them in our architecture, engineering, and construction industry is that much more viable. And so one of the studies that we're doing now is we're calling transformative materials, and we're really trying to accelerate this process by bringing on and supporting new materials from the bench scale to a prototyping to a pilot, and then beyond. So strategies for beyond, how does it impact the community? And you can see the bottom line of our graph here shows that we've really stacked the benefits from a perspective of moving forward based in our values. Next slide. So this is our graph that I always love to come back to. So when you think about an ecosystem, it's really a system of systems approach, and it ripples out, the impacts of it ripple out into our communities. So if you look at today, we can look at global materials and replace them one-to-one across regions, and there's broad acceptability, not really a problem. When we think about tomorrow, we're identifying materials that are tailor-made for existing or replacement of existing materials. And that's going to sort of, we feel, on board in 1 to 2 years. And it's going to start impacting the local socio-technical economic conditions as new factories come on board, as new materials come on board. And as that happens in the next 2 to 3 years, we imagine that they'll inspire new hubs for manufacturing, and that these materials will become more and more commonplace in the building industry. And that's when we're ripe to do what we call the quantum leap and connect these different strategies and benefits, not only from a architectural or climate perspective, but also into the economies of where these materials that Chris and Will have been talking about are developed and grown. And that kind of information can enhance local technologies, education, jobs, and training. So we're looking at this from a really holistic system of systems, community-based approach. And that's the kind of thing that environmental psychologists would tell you drives change in our thinking, in our desire to act in a different way in order to benefit and take advantage of these new technologies. Next slide, please. So this is a brief slide that talks about these ripple out impacts. So the current study that we've been working on, which is on the CLF website, is called Carbon Storing Materials. And the ripple out impacts from that have been interest by new funding partners, from Microsoft to Google to Amazon to the NSF, the National Science Foundation, Sustainable Communities grants. and the 2030 Lever for Change finalists. So there's interest in all of these different ideas that we've been studying and researching and developing over the last year. That has then led to a new study called Transformative Materials. And so where we're looking at going beyond, doing that quantum leap piece. And the ripple effect for that is really that we've been able to connect with different tribal nations and communities to see, well, what's the interest there in terms of building up new reciprocal relationships where we can start connecting an urban-rural divide. So there's interest there. And then finally, a third project that is coming together is one that looks at these pro-environmental values to understand the acceptance, the opportunities, the barriers in using these different materials in multifamily and commercial office buildings. And to really say, well, what are the values that different industries will have in order to understand them and then work through them so that we can actually get adoption and accelerate our ecosystem. Next slide, please. So if you want to find out more about our different studies or different education centers or labs, these are some of the websites that you can go to. The first one being the direct link to the paper. The next one is the Endeavor Center. This is a spotlight on Will's lab. And then my company here also has different reports on it. And with that, I think I can turn it back over to Anthony.
Well, thank you, Julie and Chris and Will for the presentations. I think that for anybody who's been listening as well as kind of monitoring the chat, this is clearly a really juicy subject that has sparked a lot of interest for a while now. And I think that I'm not even sure really how we can best be managing the chat right now, because there are so many fascinating questions that will take us hours, I think, to really fully dig into and be able to respond to. One thing that I just want to remind everybody about is that we will focus on this as a happy hour concept on July 8th at 8 a.m. Pacific. So in our next newsletter, we'll send out a link to that. So if you're interested in kind of continuing the conversation with people who are in the chat right now, or hopefully some of our speakers as well, that's an opportunity to do so. As I'm going through just looking right now, trying to field it back to the presenters, I'm curious if you, Julie, Chris, or Will have seen anything come through that you just particularly want to respond to. And if not, I can identify something. There have been a lot of questions related to the variability and soil carbon sequestration and impacts of harvesting in old growth forests and a lot of different topics. So I'd kind of rather leave it to each of you three to maybe pick up on something that's been interesting that feels like we can at least get some kind of relatively concise answer to in the next 9 minutes.
Well, I would be happy. I do think that so much of the attention for biogenic materials in the building world has been focused on timber, and I've only been able to scan quickly in the chat, but a lot of the questions there are about that and about basically not wanting to gloss over or discount the sort of significant carbon fluxes that happen when carbon comes out of the soil, there's disturbances to forests. And I think, really in our work, we've been trying to focus on biogenic materials that come from existing sources of residue, whether that's, agricultural residue, forestry residue, recycling streams in municipalities, but the carbon accounting for those materials gets a lot simpler than forests, because that grain was going to get grown and the straw was going to get cut down regardless of whether we ever make a building material out of it. Whereas with a forest, we could say, well, we just leave the forest alone and we don't cut down the trees and we don't put them in buildings, and there would be some positive carbon benefits to doing that. So the complexity that we deal with on forests, I think, gets a lot less complex when we deal in particular with residue materials. And I think, that's why we tried to make those materials the focus. And that's why I tried to show in that case study that the scenario where we didn't account for storage in wood, we only counted the emissions that came from the wood in that building, it still came close to being a zero carbon building in its upfront carbon from all of those other sort of residue materials that were in there. So, I would just like to make it, clear from my point of view that I think that's where the opportunity is. It's like that carbon is already coming out of the atmosphere. We already plant those plants. We already make that waste, and the notion of sort of using that and locking it up in buildings, I think, is really compelling and much more straightforward than thinking about it at the scale of forests.
I think we could talk about this for years, and we have, right, Julie and Chris, all together. One thing that I wanted to touch on is circularity, because I know that was brought up in the chat, and it's not necessarily our statement that at end of life that biogenic materials, all of them are circular. It's our position, and correct me if I'm wrong, Chris and Julie, that they should be, because the longer that we can store and lock up the carbon and not re-release it averts that end of life scenario where we may have more net emissions than was sequestered from the atmosphere. So, but think about this. This is 40 to 50 years into the future where technology will advance, our society will advance to the point where tools and best practices will be there. We have to create them, will be there when buildings are deconstructed so that these materials can get recertified and directly reused into buildings. So I want to kind of prime the pump here that we have a lot of work to do to make that happen. But it is definitely something that we have to solve after we all agree that using biogenic materials is the best thing to do today.
So I'll just add on to that quickly from an architectural point of view. I think
the other thing that I wanted to, go ahead, Julie.
Oh, I was gonna say, I just want to tap on that. If you're an architect designing with these materials, to have something that's designed for deconstruction and circularity has to happen at the very initial concept. That has to be one of the goals and values and vision for the project. You have to design it in at the beginning. It's not something that really adds on at the end very well. So hence the getting this notion out that we need to start thinking about assemblies and connectors and panelization that allows for that. Go ahead, Will.
I wanted to bring up the point of, there was a comment here about hemp. And so what we're seeing, and Chris has seen this the most, there are regional centers popping up that have that are converting agricultural residues into products and even growing hemp for building products. But the economics don't necessarily work out to ship those products all over the country or the continent or around the world. So what will be emerging and what we all need to really incubate are these regional centers of biomaterial manufacturing, so that what's used in Vancouver is different than what's used in Denver, than what's different than in Washington, DC, because the source of the biomass will be different in each of those geographies. So it's not as simple as saying, I want to use hemp in my building. You have to really understand where you're building your building. And this gets back to the vernacular. What is the biomass vernacular of that region? That's very important.
Yeah, or like there's the biomass vernacular, which I love and feel like that's what I've spent my career doing, is figuring that out and building in that way. But also, we have talked about and can sort of see a path for, especially when it comes to panelization, being able to think about a panel system where both the structure and the insulation and the cladding materials are all biogenic and all regionally appropriate, and yet the form that they come in is interchangeable, right? Like there's no reason that a 4x8 wall panel in Vancouver that's made out of, you know, well-sourced timber with wood fiber insulation and, you know, using the things that are there couldn't be, you know, work in the exact same way as the same 4x8 panel made in Iowa out of, you know, compressed straw as the structure and loose straw as the insulation and a straw board as the cladding, you know, that, but architecturally it doesn't have to be unique in its appearance or look or sort of performance capabilities. I think there's a way to kind of do, well, both and not sort of, you know, all standardized or all sort of funky vernacular, but there's I think a path for both things to happen and to both really concentrate on using regional appropriate resources.
Excellent. Well, maybe we can end it at that. We've got 1 minute left, and I want to make sure that everyone has time to make it to the next meeting or whatever's coming up on this sunny afternoon, at least here in Seattle right now. So just thank you again to Chris, to Will, and to Julie for joining us. Reminding everybody again that on July 9th at 8 a.m. we'll have a happy hour that's focused on this issue. We are also at the Carbon Leadership Forum continuously looking into biogenic materials across the spectrum. So keep an eye out for more resources, research, et cetera, on this topic, because we're going to be doing more about it and we're really interested by it. So thanks everybody for joining. We really appreciate having you all here today. This webinar will be available on our YouTube channel, so keep an eye out for it there if you're interested in sharing it with your colleagues. And hope you have a great weekend.
Thank you.
Thanks all.